In the previous lecture, we started the discussion on how to convert a truth table into a Boolean expression. So one of the examples that we had taken was for some system that has three input variables A, B and C with an output Y. Let us rewrite that. So for this, the Y was this was the Y. So from there, we had been able to successfully extract the canonical SOP form and the POS form. And we saw that the canonical SOP form can be implemented using only NAND gates, and the canonical POS form can be implemented using only NOR gates. So just to quickly recap that, the canonical SOP form corresponded to looking for the ones, these four. So what we got was Y equals A bar BC plus A B bar C plus A B C bar plus ABC. Now we had seen that to realize these using NAND gates, you will need one NAND gate for each of these individual product terms and one more NAND gate to combine all of these. So in total, 5 NAND gates for realizing this canonical SOP form. However, we also said at that time that the canonical form need not always be the most simplified form. So therefore, let us try and see what could be that most simplified form. So what we can see immediately is that we can group these two terms together by taking AB common. So this becomes A bar BC plus A B bar C. So if we take AB common, what we get is C bar plus C. But we know that C bar plus C as per Boolean theorem is a 1. So this becomes 1. So what we are left behind is with A bar BC plus A B bar C plus AB. So can we take something common out of these two? Can we take something common out of these two? Yes, we can. We can take the A term common. And inside this bracket, we can use the reverse distributive property where we can split them into two brackets, B bar plus B and C plus B. So B bar plus B again becomes 1. So what we essentially have is A bar BC plus AC plus AB, if you expand this. Now you can again take C common in the first two terms. That will give you C A bar B plus A plus AB. Using a similar way how we did for this particular bracket, you can again use the reverse distributive property, and what you will essentially be left behind is with two brackets, A bar plus A times B plus A plus AB. This will again cancel out to 1. So what you will essentially have over here is A dot B plus B dot C plus C dot A. You cannot simplify any further than this. So therefore, this is the simplified form. This is a simplified SOP form. Why it is SOP? Because it has again 3 product terms all combined using plus. But it is not canonical because each product term is not a function of all the input variables. This is a function of 2 variables. This is a function of 2 variables. This is also a function of 2 variables, not 3 variables. So here what we are seeing is that we have been able to successfully find out a simplified SOP form, but it is not canonical. So therefore this further reiterates our statement that the canonical form need not always be the most simplified form. So we saw that to realize the canonical form we need 5 NAND gates. We need 5 NAND gates. Now how do we realize the simplified form using NAND gates? What we essentially have as a result over here is y equals AB plus BC plus CA. So over here we get 1 NAND gate for each of the product terms. So there are 3 product terms, so 3 NAND gates. This will be AB, BC and CA, and 1 more NAND gate to finally combine these. This will be Y. So here we are using 4 NAND gates, not 5. 4 NAND gates, not 5. So therefore certainly we would like to use the simplified form as much as possible because they result in lesser amount of hardware. Now when I use the word hardware, it means the underlying electronics. So whenever you are talking about hardware in computers, that refers to the actual circuits which are inside the computer. So that's the good part. The other point to notice over here is that we started with the canonical form and we used Boolean algebra to simplify things, and we then arrived at what we claimed was the most simplified form. But what we saw was just for 3 variables. In reality, functions may be more complex. There may be more number of terms. There may be more number of variables. So therefore, what is important to remember or what is important to keep in mind is that Boolean algebra or simplifying any expression using Boolean algebra can become extremely tedious when the number of input variables or the terms increases. So So if you have, let us say, 4 variables, 5 variables, that time manually solving to simplify the expression is not easy. You will probably not even know which terms to group together, and take some things common, which will give you the least number of steps. So therefore, this manual kind of solution is not something which is desirable. As you design more and more number of digital circuits, as the digital circuits become more and more complex, as you would find in a computer, you cannot simply hope to design those circuits by finding expressions and then simplifying them by hand. That is an extremely tedious and cumbersome process. So therefore, what we need a better simplification technique. So how do we do that? A better simplification technique is available, and that is called as a Karnaugh map. And for short, it's called as a K-map. So this Karnaugh map is a technique which is not exactly an algebra based technique, but it is like a graphical or a tabular method of simplification. The name of this map, the Karnaugh map, was named after the person who developed this technique. So the first thing to know about the K-map, as I said, is it is a graphical or a tabular method of simplification. The second thing to know about the K-map is that it is used in gray code, but not directly. The gray code is implicit or indirect. The gray code is implicit or indirect. So this will become clear with time. But in the lecture when we were discussing about gray codes, I had mentioned that gray code has certain uses which we shall see in the future. Now that time has come that we will actually see how the gray code is working. So suppose we start with a simple example. Suppose we have a two variable logic function. We have a two variable logic function. Now y can be anything, 0, 1, some anything it can be. Let's not bother about that. Let us write the row number over here. The row number here is 0, 1, 2 and 3. So there are 4 number of rows totally. Therefore, the Karnaugh map technique tells you to make a table of 4 cells. So number of rows equals number of cells. In the table. So if there are 4 cells, the best way to represent a table would be a 2 cross 2, because 2 and 2 are powers of 2. This is another important thing about the K-map. It is also used in powers of 2. So here I have made a table that consists of 2 rows and 2 columns. So now the horizontal side and the vertical side. There are two. One is the horizontal side, the other is a vertical side. So I should write over here number of rows in truth table. So over here, this horizontal axis is given to one variable, the vertical axis is given to another variable. So let us give this for A and this for B. And in each axis, much like a graph, we give the forms which A and B can take. Now, what are the different forms A and B can take? What are the forms A can take? Well, depending on whether it is 0 or 1, A can take the form A bar or it can also take A. That is when A, 0 or 1. Likewise, B can also take 0 and 1. Hence, we can call them as B bar and B. This is, obviously, I am talking about the soft form. Soft form means where A bar indicates 0 and A indicates 1 and likewise. Now, 0, 0, when A is 0, B is 0, which row number it is? The row number is 0. When A is 0 and B is 0, the row number is 0. So therefore, the cell numbering we will also give as 0. When A is 0, B is 1. That is, when A is 0, B is 1, we are talking about this cell. And the cell number is the row number which is 1. Next, when A is 1 and B is 0, the row number is 2. So when A is 1 and B is 0, the row number is 2. So is the cell number. And therefore, when A and B are both 1 and 1, the row number or the cell number will be 3. So this is how you number each of the cells. Now you may ask, where is the gray code? Where is the gray code? The gray code is present in the K-map in the sense that for any given cell in the K-map, the immediate vertical and horizontal neighbors will differ by 1 bit position. For each cell, the immediate vertical or horizontal neighbor differ by 1 bit position. So over here, the binary code for 0 is 0, 0. So for 1, it is 0, 1. So these two can be neighbors. Likewise, 0 and 2. Even between 0 and 2, they differ by 1 bit position. So they are neighbors. 0 and 2 are horizontal neighbors. 0 and 1 are vertical neighbors. But 1 and 2 are not neighbors because they are differing by 2 bit positions. Likewise, 0 and 3 are also not neighbors because they are differing by 2 bit positions. Diagonal neighboring does not count. You have to go for vertical or horizontal neighbors. Is that fine? Now, let us see what y is. Suppose y is this. So now you need to fill up the cells where you want 1. So since currently we are looking at SOP form, by the way, I should mention that K-maps can be used to obtain expressions in either SOP or POS form. For the sake of simplicity, let us go for SOP at the moment. So suppose this is 1. So row number 3 has the number 1. That means cell number 3 will be a 1. So others are 0, so we don't really bother about them. So what I will see over here is I will only look for the ones and write the corresponding row and column. So this is the one, only one term. So that means y will be equal to, here we have A and here we have B. So whatever is the row, whatever is the column, they will be grouped in the form of a product. So therefore that is A dot B. This is how you read from a K-map. And this was the very basic rule in understanding what the K-map is. Now, obviously this does not say anything about simplification. It just tells you how to read the ones and assign them terms. So we can identify the ones and we can get a canonical form, and that will be a product form corresponding to the row variable multiplied by the column variable. So another example to look at is if the truth table was something like this. Suppose we have 0, 1, 0, 0. In that case, the K-map would look like this. So this is the 0th cell, 1th cell, 2th cell and the 3rd cell. So here we have a 1. So that means cell number 1 will have a 1. So in this case, I can simply read out this one and say that y will be equal to A bar dot B. This is a canonical subform. Obviously, there is no point in calling it a sub because there is no other product term, but nonetheless, it is. And you notice that even when you are looking at that row, in the subform, you are hunting for the 1. This is indeed A bar dot B. So this is one case where the canonical form is indeed the most simplified form. Now, the fun comes when you have multiple ones in the output. The fun in the K-map comes when you have multiple ones in the output. That time, there could be ways in which you can simplify. At that time, the canonical form need not be the most simplified form. So, let us see how to do that. Now suppose I have a truth table which looks kind of like this. So let us say we now have this truth table. So the row number again we'll put. So in this case now the K-map would look something like this. The cell numbering will be 0, 1, 2 and 3. So the 1th, 2th and the 3rd cells are 1. Now we have to ask ourselves, how do we simplify this? One way obviously is to read out each of the terms corresponding to the 1 and then showing them in the canonical form, and then using Boolean algebra. But then there is no point of talking about a K-map. Solving with Boolean algebra is something that we want to avoid. And the very reason we are using the K-map is to try and see whether it can give us a one-shot simplified form of the output. We are looking for a way through which we can get a one-shot most simplified form for y. So now, since we have multiple ones, we have to start grouping them. Because grouping in K-map is kind of like taking something common between two terms in Boolean algebra. So therefore, do grouping for multiple ones. But you cannot do this in any manner. You have to be very careful. So, when you are grouping for multiple ones, you must group them, group one with its vertical or horizontal neighbors. The second rule is you cannot just group them anyhow. The group size has to be a power of 2. The group size has to be a power of 2. That is, well, 1 is also a power of 2, but then 1 is not a group. So you can make groups of 2, 4, 8, 16 and so on. And the third rule is that make as many groups of 1 as needed until each one is a part of at least one group. So once all the ones are part of one group, there is no need to make more groups. No need for more groups. So therefore, let us apply these 3 rules to this K-map. I now have multiple ones. I could make, let us say I take this one, the one in the 1th cell. So its immediate neighbor is the one over here. I can group these two and make a group because that's allowed. It's a horizontal neighbor and the group size would then become 2. So suppose I do this. I call this as group number 1. Now, what am I noticing? This one is left behind. It is not yet grouped. So therefore, this one I can group with this one. This one I can group with this one. And then what I am seeing, all my ones are grouped. So therefore, let us call this as group number 2. Right? So, we have made the groups. Then what? The next rule is, look for the common variables in each group. And those common variables will make a single product And last but not the least, all groups to be combined using a plus. So let's apply the fourth step. Let us look at group number 1. In group number 1, we have these two ones common. So on the horizontal side, we see A and A bar. So neither of them is common. But in this group, since it is one row, here B is common. So the common variable for group number 1 is B. Let us now look at the group number 2. Over here in the vertical side, we have B bar and B. So they are not common. What is common in this column is A. So therefore the common term for group number 2 is A. So what you notice is that each group is giving you one term. So therefore the final expression will be y equals each result combined using a plus. So therefore it will be A plus B. That's it. And as you notice, it is indeed the OR. It is indeed the OR gate. Notice one thing, that is the K map is expected to give you the most simplified form. You should not have to apply even the smallest amount of Boolean algebra from the expression that you get from the K map. That means if you have to apply any amount of Boolean algebra on the expression you get from the K map to simplify it further, that means you have not done something correct. You have not used the K map in the most proper manner. That is very, very important. Let us take one more example. Let us say we have the truth table which looks like this. Let's have the row numbers. So in that case, the K map would look like this. The cell numbers will be 0, 1, 2 and 3. So the ones will be the 0th, 2th and the 3th cell. So how do we make the groups? One group we can make here. Let's call this as group number 1. We can make one more group. We'll call this as group number 2. So the common terms corresponding to group 1 will be A. And for this, it will be B bar. So therefore, we get y equals A plus B bar. This is how we combine the results from each group. I hope that is clear. So here, one thing that you have, let us say, you can also have a case, that's a very peculiar case, where you can have all ones. Now suppose you have a case where all the entries are 1. 1, 1, 1, 1. In that case, the K-map will look like this. So in this case, what you can do, you can actually make a group of 4. You can make a group of 4. So then over here, you have A bar, A, B bar, and B. When you make a group of 4, you may ask yourself, what then will be the result? There is no common term, neither in the vertical or the horizontal axis. So no common terms. Implies the answer is 1. Because here it is all equal to 1 no matter what. And since we are using it in a sub form, this is what we get. There is no common variables, means the answer will be 1. Let us now very quickly take a look at how to use a simple K-map in the pos form. The underlying principles remain exactly the same, except that now A equal to 0 indicates a 1 and A equal to 0 indicates A and A equal to 1 indicates A bar, and like that. And secondly, we have to make groups of 0 now. We have to now make groups of 0. But the same rules apply. You can make groups of zeros in either vertical neighbors or horizontal neighbors. But over there, each group will correspond to a sum term. Each group will correspond to a sum term. And all groups have to be combined using dots. That is how you get pos. So now, supposing I have something like this. Let us take a very simple example. I have this truth table A, B, and Y. So suppose I have over here this, and I want to use it now in the pos form. Now, the K-map will look something like this. If I want to keep my cell numbers as 0, 1, 2, and 3, the axis will still be A and B. But 0 means A and B are both 0. So that means now this will be A and this will be B. This will be A bar, this will be B bar. This will now change, because notice, let us say for 3, it is A bar and here it is B bar. Because A is 1, B is 1. So you get A bar and B bar. Now what we will do, we will fill in with zeros, because we are now hunting for zeros. So 0th, 1th and 2th row, we will fill with zeros. Alright. Now next rule, make groups of zeros. Let us say I can group these two zeros and call it as group number 1. I can group these two zeros and call it group number 2. So over here, corresponding to group number 1, the term will be, the common term will be the variable which is common, that is A. And for group number 2, the common is B. So therefore, Y will be equal to the combination of these two using a dot, that is A dot B. This is the pos form. So this has to be clarified in more detail by solving more and more practice problems. So what did we discuss about the K-maps? We said that in K-maps, you can group ones or zeros with horizontal neighbors and group size should be the power of 2. Another important thing that you should remember is that wherever possible, group size has to be maximum. Now let us say if you have a place where you have 4 ones, you can make 2 groups of 2. But it will be easier if you make it 1 group of 4, because that will give you a more simplified result. So, to summarize what we learned in this particular lecture is that to overcome the problem of having to solve for cumbersome Boolean expressions from canonical form to the most simplified form, we go for a technique that is called as the Karnaugh map or the K-map, which is used in the implicit gray code, and we fill those K-maps with ones or zeros depending upon whether we want it in the sub form or the pos form. And the important thing to know is that we solve the K-map by trying to group ones which are vertical or horizontal neighbors, and we have to keep making groups until each one or each zero of that K-map, as per our requirement, should be a part of at least one group, some group. So never should it happen that all the ones are parts of more than one group. There should be some ones which are part of at most one group. Otherwise, what will happen is that you will lead to additional terms. It might lead to additional terms, and therefore it is not wrong, but it may require more number of gates. So therefore, we shall continue this discussion on K-maps in the next lecture with more examples and discussion on how to use K-maps for systems having more number of variables. Thank you.